right, you guys, it's 8 o'clock, so we're going to get started. I'm mic'd up today because hopefully we record. And if it's on the microphone, you can hear it better. Okay, so today and Thursday, we're going to take our time and just cruise through Chapter 2. This is all biochemistry. It's like intro to biochem. Those of you that took Biology 1441 or Biology 1341, which is cell and molecular biology, that is this class, or that class in this chapter. Okay, the first 5 chapters or so, they took a bunch of that and stuck it in here. Are any of you guys, I don't know your schedule, are you in A and P now? Or did you already take that, or are you going to take that? Okay, so this is all going to be in A and P again. So you need to know this over and over and over and over. So we're just going to kind of take our time through it. I really don't like your book. This chapter is terrible. There's so many things not correct in this chapter that as a biologist, I was just shuddering like, oh. So I'm going to point out, because I'm a biologist, the correct way that all scientists in the world say this. I don't know. I'm definitely going to call Marjorie and be like, what are you doing, lady? She doesn't know apparently what the word molecule means. I'm like, there's all these reviewers. Nobody caught any of this. She's not going to like me when I write this email. So I want to make sure you know some of the proper ways we do the words. If you look in your book, this chapter is basic chemistry, macromolecules, which is biological molecules, and then in the end it's cells. I'm not even touching that cell part because it's really just basic. I mean, we're going to get into the cell in much more detail when we go through all the little microorganisms. So this is what we're doing in this chapter. Okay, so today we're just doing 2.1. Thursday we'll do 2.2. Okay, so this section, really basic chemistry, like subatomic particles and bonds. Just because it's basic doesn't mean it's not important. Review. Okay, these are basic definitions, but in case you don't remember this stuff, when we say matter, we're talking about anything that takes up space and has mass. So if I pick up this can of LaCroix, you're like, oh, of course that's matter because you can see it, you can feel it. It takes up space, you can feel the mass. But don't forget that a microorganism is matter. The air you're breathing is matter, even though you can't see it because it's so small. Those are physical items that take up space and have mass. Okay, in this section, we're going to be talking about atoms. You have to know what an atom is to understand this, or you're going to be confused. It's defined as the smallest unit of matter that retains the property of an element. Okay, so we got to go through all that. But essentially, what it's saying, it's this tiny unit of matter that we cannot physically pull apart. Now, keep in mind, because some of you out there going, well, if you were at CERN and you're in the particle collider, you could do that. Yes, you could. We mean naturally, in nature, atoms don't just come apart. Okay? And there are many subatomic particles and an atom. We are learning the basics, a proton, a neutron, and an electron. That's it. Because that's what applies to microbiology. The first thing you need to know, and this is so important, especially for anything in science, is structure. Structure always tells us function. A thing is shaped a certain way to do a specific function. That's true of all the bones in your body, your muscles. That's true of an atom. So you have to understand the structure. The center part is called the nucleus, and you should know that inside the nucleus are protons and neutrons, the two subatomic particles. Okay, electrons are all the way on the outside, okay, very, very, very far away, moving around. Electrons never stop moving, okay, and they're moving around in these defined spaces, which we'll talk about. The next thing you have to know are the charges. Protons, and I underline this for you, begin with a P and they have a positive charge. That's easy. Neutrons are neutral. That means they're not positive or they're not negative. So again, I underlined the NEU so you can remember that, because what students always do is they put a negative charge on that because it's next to a proton. It is not. It's neutral. Okay, the one with the electric charge is the electron spinning all the way on the outside. So these have an attraction to each other. They're not ever going to touch each other. If they do, that is how the atomic bomb works. We don't want that happening, right? We don't want these things touching. So they don't touch in nature. We would have a lot of explosions. And that's not how it works. Okay, so the electrons want to be close to the nucleus, but they're not close to it. They're just attracted to it. Okay, and notice, electrons are negative. If you have some basic physics, you know that positives don't like positives and negatives don't like negatives. So even though they're spinning around out here, they try to stay away from each other. It's a little tricky. So even though this marker and the desk you're sitting in and anything solid feels solid to you, it's moving. Okay, so it has a vibration to it because these electrons, which make up all the little parts that come together for that, are moving. It just feels dense to us because there's so many of those atoms packed close together. Okay, so review slide. Protons are positive, neutrons neutral, electrons are negative. Okay, and I said they don't touch. This is the periodic table of elements. You don't have to memorize this. This is not biochemistry or chemistry. If you need this on the test, I would give you this information. There are some things you have to understand when you're looking at it. You'll see the symbols. You don't have to memorize those, don't worry, but here, just to give an example, here's carbon for C. You'll see a whole number at the top, 5, 6, 7, 8, 9, 10. That's called the atomic number. That tells you the number of protons for that specific atom. So if I had all you guys right here and I counted out your protons and every single one of you had 6, I would define you as carbon. I'm going to say, okay, you guys are carbon. Then I come over here and like, oh, wait, you guys don't have 6 protons, you have 5. Well, I'm going to call you boron. So that is how we define an element. That is how we define the atom, the number of protons. And I'm so happy that some of you actually started to write that down because it's incredibly important. And in my class when I teach this, I'm like, that's really important. And students are just like, write it down, write it down. Okay? So it's important that you understand that an element is defined. This is how we classify. This is how we make the whole table by the number of protons. Okay? If you didn't know that, that's the atomic number. And yes, you should know that. What is the atomic number? Number of protons. You're going to see why that's important. Any question on that? Does that make sense so far? So we don't care about the number of electrons. We don't care about neutrons. The thing that is going to define you as carbon or oxygen or iron is going to be your proton number. The ones that you're really going to care about in any of your biologies, your anatomy, physiology, your micros, is hydrogen, carbon, nitrogen, and oxygen. Okay, those are the big players because that is what we are mostly comprised of. When you look in the mirror and you see your beautiful face, you're looking at a lot of carbon, hydrogen, oxygen, and nitrogen. Damn, this oxygen looks good on me today. Okay. So what happens if you guys are hanging out, you're carbon, you're doing your thing, and you lose a proton? You're no longer going to be carbon. You're now boron. You got to go to the other side of the room. Okay? You're no longer who you are. You've changed yourself. You become a new element. Okay, so that can happen. All atoms can lose subatomic particles. Okay, that's how X-rays work. So that's a normal thing. They can lose their... Okay, now it's not generally you're not going to lose a proton. They're mostly stable. Okay, so just as an example, nitrogen has a atomic number of 7. So it has 7 protons. If it loses one, it's going to be carbon. So you can change the proton number. You're going to change that element. What happens if you lose a neutron? Okay, the one that's sitting in the center of the nucleus. It's neutral. What's going to happen to it? You're going to create what's called an isotope. Okay. We actually weigh out our atoms. We don't weigh them out the way that we would weigh ourselves on a scale. We do it a little differently because those subatomic particles are so small we can't weigh them. But the way we do it is we just count them. We just say, oh, well, one mass unit for an atom is an atomic mass unit. We would say 1 proton or 1 neutron is a 1. And this, don't worry about all this. But anyway, so neutrons, all you think they're going to affect if you lose a neutron is the mass. Okay? It's like losing a few pounds. It's all right. Okay, so they're elements. You'll still be carbon if you lose your neutron. Not a big deal. Okay? You're just going to change the mass. In medicine, you're going to hear about radioactivity, okay, radioactive isotopes, because we use this a lot in medicine. All that means when we say something is radioactive is that they easily lose a subatomic particle. So in this case, it could be a neutron. There's many different types of subatomic particles, right? So let's just say, however, the one that you're losing is a neutron. Carbon-14 is radioactive. If it loses a neutron, it becomes carbon-13. Okay, the 12, the 13, the 14 are telling you the weight. That's what it is. That's not, remember, what is the atomic number of carbon is 6. They still have their 6 protons. So you see that 6 protons, 6 protons, 6 protons. It's just the number of neutrons. So change neutrons, you become an isotope. And stop me anytime you have questions. This is important. Let's get back to the atom. Okay, so we have protons, we have neutrons, we have electrons. When we say atom, we are saying the number of protons is equal to the number of electrons. Okay, so that means if you're carbon and you have 6 protons, how many electrons do you have? 6. Okay, so that means that you have equal number of charges. So overall, if you're an atom, what's your charge? You're neutral. Okay, so there's your protons, there's your electrons, you're neutral. That's how you start off as an atom. But you might not be happy, because there's this rule that we've learned. And we make rules and we make up laws because we're humans and that's what we do to observe and describe what we're looking at. So we've realized that electrons are very lonely. They like to hang out in pairs. Even though they're both negative, they like to be in pairs. Okay, a lot of things in biology like to be in pairs. So it wants sometimes to add an electron or lose an electron, okay, that are spinning around this atom to make sure that it has the right number on the outside. So if that happens, if it loses or it gains an electron, okay, those are called ions. So what happened if you change the proton number? Change the element. You change the neutron number, you're an isotope. You change the electron number, you're an ion. Okay. So if I took this away, what's the charge of that? It's no longer an atom, it's an ion. What's the charge? Yeah, so we would say that's +1. What if I did that? Now what is it? +2. Okay. That is called a cation. It's positive. Okay, so cations have positive charge. Notice the word ion is in it. Okay? So it's telling you it's an ion, it has a different number than the atom, okay, and it's positive. What if I added some electrons? Now what's the charge? It's -2. Okay, that's called an anion. If you have more electrons than protons, it's a negative charge. That's an anion. Okay. So atom, equal number. Your atomic number is going to equal your electron number, protons and electrons. If you lose any electrons, you gain any electrons, you're now an ion. You're either a cation or an anion. So far, so good? Okay. So where do these ions come from? Okay, normally what can happen is you have another atom next to it that strips the electron away. Okay? Or it can be one of the ones that takes an electron from somebody else. Okay? So it does that because of this property called electronegativity. Okay? Electronegativity is a property that is defined by each specific type of an element. It's nothing we can change. Okay? So don't think like, oh, you can change the electronegativity of carbon or hydrogen or nitrogen. It is set because it's due to the structure of that atom. Okay? What it is how strong can you pull an electron towards your nucleus. If I'm really electronegative, I can strip an electron from somebody else and take it. Okay? So that's how they're formed. That's how we make an ion. So again, if you lose your electron, electrons are negative. So if you get rid of a negative thing, let's say you get rid of the habit of procrastination, that's a negative habit. You're now a positive person. Okay? Positive charge, cation. If you gain the electron, it's negative. Okay? Think of it like reducing your charge. Okay? You were nice and neutral, now you're -1, you're -2. That's an anion. Here's a way to remember cations are positive, because cats have pos, positive. Okay? I hope you remember. So looking at this one, these are your proton charges. These are your electrons. Is this one a cation or an anion? That's a cation. And then what's the charge on it? It's a +1. What about this one over here? It's an anion. Okay, so you're counting up all your numbers. And what's the charge on that one? Is it -2? Yes. Okay. negative 2. Okay. And this gives you an idea of how electrons are oriented around the nucleus. They can't all be close to it, even though electrons are really attracted, because there's not enough space. So they kind of move out in these areas that we call shells. So let's talk about these electron shells. Don't get too stressed out about this or worry too much about electron shells or orbitals. I'm not even really worried about you guys knowing orbitals. You'll get that at some point. It's not inherent to microbiology and to nursing. You're not going to get a patient and be like, hold on, let me check your orbitals. It's not going to matter. Okay. But this space that's the closest to the nucleus, okay, which would be this first one, it can only hold 2 electrons. It's a really small space. So only 2 little electrons fit in this area. So this area, which by the way it doesn't exist as a physical thing. It's just a space that we've defined. Like we call this space room 119. Okay, so they call this space shell 1. Okay, so shell 1 is small, it has 2 electrons. That one fills up first. Okay, the next space out is shell 2. We're not going to go beyond shell 2. There's multiple shells. We're just going to stop at 2. 2 can hold up to 8 electrons. This is just the basics. We're not getting into heavy chemistry when technically you can jump out to shell 3 and come back to 2. We're not doing all that. We're just going to say 8 electrons. Okay? So 2 here and 8 here. Just because you can put that many electrons in the shell doesn't mean you're going to. You might not have that many. What if you're hydrogen? Hydrogen, let's say you have an atom. Its atomic number is 1. How many electrons does it have? 1. Okay, and what's cool about hydrogen, it has no neutrons. It's just a proton and an electron. Okay, so it has 1 little electron out here in its shell. Let's look at carbon. Carbon's atomic number is 6, 6 electrons. So it puts 2 into the first shell. Everybody, heavy math. 6 minus 2 is 4. Good job. Okay. So 4 in the outer shell. Right? And you're getting the idea? Okay, so this is what I was telling you about ions. These are atoms, right? But they're not happy this way. Hydrogen is not happy only having 1 electron out here. So it's going to find a way to put another electron to complete that shell, to pair up that electron. So it either can become an ion or it can form a bond. Okay, it can share an electron. Okay, carbon wants to fill this outer shell. How many electrons would it need to do that? It has 1, 2, 3, 4. Remember, there's 8 total, so how many does it need to put in there? 4. Okay. So this is, again, a picture showing you, this is a little bit more complex. We're just going to look at it like this, where you just put the nucleus and then draw the circle, the lines around it, shell 1, shell 2. Okay, 1 proton, 1 electron, and then here's carbon, okay, with the 4 on the outside. There's what these actual spaces look like if you get into them, like shell number 2. They move in these specific paths. Those are called orbitals, but like I said, we're not going to worry about those, but just so you know what they are. So atoms, they want to complete that outer shell. The outer shell is called the valence shell. So whether it's shell 1 for hydrogen, it could be shell 2 for carbon, it might be shell 3 for, say, magnesium. Okay, so it just depends on the element. Whatever one is the outer one, they want to complete it. They want to fill it up with electrons. If it can hold 2, it wants 2. If it can hold 8, they want to put 8. Okay. So how are they going to do that? They could become an ion. Right? Hydrogen could just lose an electron. It can gain an electron. I'm not going to ask you chemistry questions like, is this atom going to gain or lose an electron? Is it going to form an ionic bond or a covalent bond? I'm not going to ask you those questions. Okay, you'll be tortured when you take chemistry. I don't have to torture you. It's biology. Okay. So they can do that. They can gain or lose an electron. Okay. The second way to do it is share. Okay, they're very nice little substances. They share their electrons. When they share, they form specifically a covalent bond. Okay, so that's a bond that you're going to learn a whole heck of a lot about. Okay, so we have valence shell. The electrons that are in the valence shell are called valence electrons. That is what that atom already has. Okay, so if you're hydrogen, your valence electron is 1. If you were carbon, your valence electron was 4. Right? That's how many they have. There's another term that gets a little confusing. Okay, bonding capacity is how many bonds could hydrogen form or carbon form. Hydrogen, if it was going to share one electron with somebody, that would be one covalent bond. Carbon, remember, had 4 spots to fill. That's the bonding capacity. So bonding capacity tells you how many electrons do you need to fill the shell. Okay, why is that confusing? The other word for it is valence. So somebody might say, what's the valence of nitrogen? That is not the same thing as asking how many valence electrons does nitrogen have. Let me see. Let's go back to this wedge. Okay, so let's look at nitrogen. How many valence electrons does nitrogen have? It has 5 valence electrons. But if I said to you, what is the valence of nitrogen? It is not 5. What is it? It's 3. Valence is how many it needs to fill the outer shell. It needs 3 more. Remember, so 8 is the outer shell. It has 5. That's the valence electrons. It needs 3 more to fill it. That's valence. So that's 1, 2, 3. So bonding capacity and valence are the same thing. I think it's better to just call it bonding capacity. How many bonds is it capable of forming? 3. It can form one here, here, and here. It can share one here, here, and here. Does that make sense? So you just got to be careful on the test that you're reading carefully. Slow down. You have 50 questions. You have an hour and 20 minutes. That's a lot of time. Okay. So how do you determine the bonding capacity? You would look at the atomic number. Okay, so we said carbon is 6, oxygen is 8. You can draw it out. Here's my nucleus. Here's my first shell. I'm going to put 2 electrons in the first shell for oxygen. So 8 minus 2 is 6. So I'm going to go out here and go 1, 2, 3, 4. What is it? It's 8. 5, 6. Okay, so that is how I would set up the electron configuration for oxygen. I would have to give you the atomic number, okay, on the test. You just have to know how to fill this out. Okay, put 2 electrons in the first shell. Whatever I have left over, I put into the second shell. There's 6. So what is the number of valence electrons for oxygen? 6. What is the bonding capacity of oxygen? 2. All right, you've got it. Okay. So does that make sense how you would figure that out? Okay, that's it. Now we get to the important stuff. We've mentioned these bonds. I've talked about an ionic bond. I've talked about covalent bond. We're going to actually really look at them. So bonds are a way that we fill these outer shells and make everybody happy. There are some atoms that have their shells all filled up. They're called the noble gases. They're inert, which means they're not reactive. It also means they're incredibly boring. We don't really like them in biology. Here's the 3 bonds you're going to learn. Okay. A note that's important. If it is in your textbook, but I did not teach it, you're not responsible for it. Okay? So if you're reading your book and it's saying, oh, van der Waals forces, but I didn't talk about those, then don't worry about it. I'm only going to test you on what's in your PowerPoints and what I'm talking about in lecture. Okay. I know those professors are like, oh, on page 72 in that one chart and that one line and that one thing, that's what you were supposed to know. Okay. I'm going to tell you what you need to know. Okay, so these 3 bonds. Covalent bonds in biology are the strongest bonds out of these 3. So I like to say that that's like marriage. It takes a lot of energy to make this bond. It takes a lot of energy to break the bond. You can get a divorce. It's expensive. It's also expensive to break this bond if you're talking about energy. So yes. Ionic bonds are based completely on attraction, a positive and a negative charged attraction. So this is dating. Okay, so you can ask somebody if they want to go on an ionic bond with you for Valentine's Day. They'll be like, what? Like, ugh. Hydrogen bonds, don't do this for Valentine's Day. This is not romantic. These are one-night stands. Okay, don't do this. Okay, these are very weak interactions. Usually when we talk about hydrogen bonds, we're talking about water molecules, which are moving a lot. So they form a bond and they break it, form a bond and break it. It's very transient, might last fractions of a second. There are hydrogen bonds that are in place for a long time, like in cellulose and DNA, that can be strong, but alone, one bond is very weak, which we'll talk about. So let's start with ionic bonds. So this is a charge attraction between two ions. Okay. So let's say you guys over here you're a cation, so what charge are you? You guys are positive. You guys are going to be the anion. What's your charge? Negative. Okay. You're already an ion. You already exist in nature as an ion. You're floating through the air and you bump into each other. It's love. Okay. It's attraction. You're going to stick together. You're just going to sit next to one another. You're not sharing anything. Remember, your outer shell is full and your shell is full. You just happen to be positive and you're negative. So you guys just sit next to each other. Okay, so you could just sit next to somebody at Starbucks and be like, it's just an ionic bond, relax. Just sitting here, just attracted to you. Okay, so that's all it is. They're just hanging out next to each other. Okay. This is important, and this is one of the things I think the textbook messes up. Exchanging that ion, or that electron, let's just say that you guys over here had an extra electron that you wanted to get rid of. You had a third shell with one electron, and you guys had a second shell with only 7. So what happened is you guys came over and took the electron from this one. That would be great. Now your second shell is full, and your second shell is full. You're just positive and you're negative. That exchange of the electron is not an ionic bond. That's not an ionic bond, because you could already just be an ion and form an ionic bond. Okay, so this exchange that happens, that's not the bond. The bond is after you're already an ion, you just happen to hang out next to each other. Does that make sense? Okay, so you can form an ionic bond without exchanging the electron. It just so happens in nature a lot of time, if you're going to exchange the electron and you become positive and you become negative, you're already next to each other. You're probably going to hang out and form the ionic bond. I just want to make sure you know that this happening is not the ionic bond. Here's a nice example. Again, I like to give you a lot of good material to discuss with people over lunch, so you're very interesting. So if you happen to be putting salt onto your food, you can tell them all about this process today. Here's sodium. Okay? This is an atom, and chlorine, which is an atom. So protons and electrons are equal. This is an example of, on the third shell, sodium has 1 electron. That's just how it works out. Chlorine, okay, on its third shell, has 7 electrons. So if these guys bump into each other, it makes a lot of sense. It works out energetically that this electron will transfer over to chlorine. Everybody's happy. Sodium now is an ion, Na+, because it has an extra proton versus the electron it lost, right? It doesn't have that negative charge, but it still has a proton down here, so it's +1. Chlorine, or chloride, is now a full shell out here. It has 8, but it's a -1, because it has 1 extra negative electron compared to the protons. Everybody's happy. So that exchange is not the ionic bond. If they stay next to each other, then it's an ionic bond. Make sense? Okay, who's the cation? Sodium, yeah, and chloride is your anion. Just in case, you could read, but maybe not. Something to keep in mind. Did the atomic number change on these ions? No. What does the atomic number tell you? Protons. So be careful. If I ask you on the test what the atomic number of sodium is, you cannot count the electrons, because it's not going to tell you. You could count the electrons and then be like, wait, I got to change it because the electrons don't match the protons. You could still figure it out. You just have to know. Over here, you could just count the electrons and be like, oh, it's equal. That's how many protons you have. Here's a fun joke for you. I like this because they can't get away. It's like, ah. Get it? Okay, I have a better one. Not for that. Okay, covalent bonds. This one is all about sharing. Okay? Sharing electrons. So keep in mind when these atoms are interacting, who's interacting is just the electrons. Okay? We shouldn't have protons and neutrons from different atoms touching each other ever. Okay, this is 2 atoms that share electrons to complete their shell. This is a much stronger bond because instead of you guys just being next to one another, you're actually going to be so close that your spaces, those shells, have to overlap. Okay, so what has to happen? Can I have like two people just like stand here for a minute? Since you guys are just right here, can you just stand up over here for a minute? You don't have to do anything but just stand like right here next to each other. You're going to be my two nuclei. Okay, so you're an atom and you're an atom. I'm just going to do one electron to give you an example. They'd be sharing two electrons. The way they share it, I'm an electron in the outer shell, and let's say I belong to you. I would spin around you. I'm going to have to go between you. Spin, spin, spin. But then she's sharing me, so I'm going to go around this atom. So I'm going to spin around her. I'm going to get dizzy. But you get the idea is if there was another me, there's two of us, right? Two electrons taking turns around you guys. So I spin around you, I spin around you, I spin around you. Right? What is my charge as the electron? Negative. So if there's another one, do you mind standing up since you're over there? Just stand right there, yeah. Okay, let's say she's also an electron. So you're negative also. So she's over there and I'm over there. If you just froze us for a second, we'd be kind of equally distributed, wouldn't we? Because I'm negative, you're negative, you guys have the positives, we'd all be kind of equal. But remember, you and I never stop moving. We're very busy. We never stop. So at some point in time, we could both end up over here together, and you would be slightly negative, and you would be slightly positive. Okay, that's going to come into play later. Thank you, guys. So that's what we mean when we say sharing electrons. Does that make sense a little bit? If we want to share just one pair, like this is hydrogen, okay, and here's an electron, and here's another hydrogen. So there's me and you, the electrons. We're going to spin around this one, then this one, then this one, then this one. They're just constantly moving. A double bond is if you share more than one pair. So here's a pair, and there's a pair. Okay, carbon is super cool. We'll talk about carbon because it can form 4 covalent bonds. So it can share 4 electrons, pairs. A double bond is obviously going to be stronger than a single bond because you need even more overlap, okay, for 2 sets of electrons to be going around both of you. You have to be really close together for the electron to circle both atoms. That's going to drive me crazy. There we go. Very important definitions that your book screwed up. This is like Bio 101. How did they mess this up? Okay, a molecule. The word molecule means things. This is why I get really frustrated. Words in science are very critical. It can mean life or death for a patient. You've got to know what words mean and use them properly. Okay, there's a saying, say what you mean and mean what you say, right? You have to be very clear in medicine. Okay, molecule specifically means it's telling you covalent bond. That is the definition of a molecule. So if somebody tells you I have a molecule of this, they're telling you I have a bunch of atoms that are bonded together through covalent bonds. Okay, 2 or more atoms that are sharing covalent bonds, are sharing electrons. So if I said to you polar molecule, I don't have to tell you it has covalent bonds, that it's strongly bonded together. You know that because you know the definition of molecule means covalent bond. So the bond type is important. It doesn't matter which elements you're using. It could be, we would say, molecular oxygen, molecular nitrogen. Why is it called molecular? Because they're molecules. They have covalent bonds between oxygen, covalent bonds between nitrogen. Water is a molecule because there's covalent bonds between hydrogen and oxygen and the other hydrogen and an oxygen. In that case, there's a covalent bond here and here. Compound is another word that is completely different from molecule. Compound is a word that defines something as more than one element. It doesn't matter what kind of bond it is. It's just any substance that is comprised of more than one element. So if I look at water, it is a compound because it has hydrogen and oxygen. This is sugar, glucose. So there are lots and lots and lots of compounds that are molecules. Okay, so all compound is telling you is that you have more than one element. Why we even talk about that in chemistry is because nature is super cool. If we go back to sodium and chloride, sodium is this dull metal. Chlorine was used as a gas in wars, to pretty much, it turns into bleach in your lungs, and it's really nasty stuff. So I give you this metal, or if I give you this substance that's going to burn your inside of your lungs, you're not going to want that. But if you put sodium and chloride together, you have delicious salt. Okay? That's why nature is so cool. Those are compounds. So this is really neat for us to say, this element and this element come together, they form a compound that's completely different of other of these elements. So compounds are cool. So sodium chloride, okay, something like this, oxygen, that's molecular, nitrogen, not a compound, okay, because it's only oxygen, only nitrogen. It retains the properties of oxygen or nitrogen. Does that make sense? Okay, so molecule, covalent bond, compound, we don't care what kind of bond, it's just multiple types of elements. Okay, more about covalent bonds. You knew there was going to be more to this story. Are you guys remembering this from biology a little bit? Yeah, you're having flashbacks and nightmares? Okay. Two types of covalent bonds, nonpolar and polar. Nonpolar are the ones that do not have any charge associated with them. Okay, and that was kind of what I was showing you in the first example when you were on the one side as the electron and I was on the other. We were equally dispersed around our atoms, so our negative charges were equally dispersed. Okay, in that case, there was no charge. Okay, the two atoms were sharing the electrons equally. What does that mean in terms of chemistry? All right, they're not like, hey, you take the electron. No, you take it. You take it. They're not really sharing. It's physics, right? It's the attraction. It's the pull of it. So what it means is those protons that are in the center have the same force that we call electronegativity. It has the same force to pull the electron to it as this atom over here had. So they have equal electronegativities. This one can pull the electron, but then this one is equally as strong as saying, nope, I'm going to pull the electron. So it pulls this way, then it pulls that way. It pulls this way, then it pulls that way. So even though electrons are constantly moving, it's equally spaced out. Okay? Those are nonpolar covalent bonds. Why do we care? Whether you're a nonpolar molecule or a polar molecule defines how you interact in the body. Can you cross a cell membrane? Okay. Are you going to dissolve in the blood? Can you cross the blood-brain barrier? Okay. If you're a drug, we need to know, where do you need to go in the body? How are we going to make this work? Okay. So it's important for physiology. Polar covalent bonds do not share equally. The best example is water. Okay. When you hear the word polar, you automatically think of water. Now you know why. Okay. It's a polar molecule. So again, that word molecule is telling you covalent bonds. This means electrons are not shared equally, so they are charged. This one molecule of water has a charge associated with it. Let me see. Here, I'm just going to show you this picture. I'll go back, but this is water. Here's oxygen, and here's hydrogen and hydrogen. This is how it's structured. We have one covalent bond here. So remember, hydrogen's bonding capacity is 1, oxygen was 2. So it shares a pair here with this hydrogen, and it shares a different pair of electrons over here with this hydrogen. Hydrogen is small, and it has weak electronegativity. Oxygen is bigger, and it has a much stronger electronegativity. So who can hold and pull that electron more, oxygen or hydrogen? Oxygen. Okay, so oxygen has that force, a greater electronegativity. So it pulls the electrons over more. Okay, so does somebody else want to come stand up so I don't torture the same people? Oh, you're going to do it again. She's like, please don't make it. You can do it. Okay, so this time it's going to be a little different. You're going to be oxygen and you're going to be hydrogen. I'm still going to be the electron. We're only going to do one side. So what ends up happening is I'll go around hydrogen, okay, but she doesn't have a strong electronegativity. The force that's pulling me more, you have more positive. You're going to pull me this way. So I'm going to circle around oxygen a lot. Be like, hey, hydrogen, nope. I was like, I'm still around it. No. I'm just going to hang out over here. So most of my time is spent with oxygen. So what's going to be the slight charge on oxygen? Negative. What about you, hydrogen? Yeah, hydrogen is a little bit positive. Okay, the difference, what I really want to highlight is I'm still going to go back over here. I still like you. coming over. So you could freeze at any moment in time, and I might be over here. You might be slightly negative and you slightly positive. It just so happens when we do studies, most of the time I'm over there. Okay, you guys can sit down. Thank you. That's a polar covalent bond. The terminology is very important to understand. This is called a partial charge. It's partial because the electron never stops moving. So most of the time, the charge associated with the electronegative atom in the molecule is negative. Most of the time, the charge associated with the less electronegative or the weaker electronegativity is positive. So what you're going to see, and this is so small, let's attempt to draw this first. Kind of looks like that. That's delta. That's a symbol telling you partial charge. Why do you need to know that? Because this is not an ion. Okay, if I have an ion, I have a plus drawn on it because it is telling you that has an extra proton versus an electron. It has a +1 charge all the time. It never changes because of the subatomic particles it contains. I do not draw water with a charge. I just say H2O, 2 hydrogens, 1 oxygen. Okay, the subscript always tells you how many in the molecule. So that's the difference between an ion that has a charge all the time and a molecule that's polar that has a partial charge associated with it. Does that make sense? A little bit? Okay, so let me come back and make sure we got all this. In biology, the big ones that we care about, oxygen, I'm actually going to write it like this. This might help you remember it. Okay, this is nitrogen, this is oxygen, this is carbon, and this is hydrogen. These two are strong electronegativity. Okay, really, really, really strong. Really pull the force. This one, weak. Okay, we don't actually see this based on bonding capacity. Everything branches off of carbon because it can form 4 covalent bonds. So carbon is what we call the skeleton or the backbone of all molecules. That's the whole field of OChem. Organic chemistry is based on carbon-based molecules, which is your body, right? So again, when you look in the mirror and you're looking at all the beautiful carbon in your body, you have carbon, and then these 3 elements are always branching off of it. So you have a lot of bonds with carbon with these 3. Nitrogen and oxygen don't go together very much, okay, in the body because they don't complement each other's bonding capacity. So we won't see these guys attached, but we will see oxygen with a carbon or oxygen with a hydrogen. If we see that in a body, what kind of covalent bond is it going to form? Polar, because these are strong and these are weak. We also see nitrogen with carbon and nitrogen with hydrogen. Those would be polar covalent bonds. So if I had a molecule and it had a bunch of carbon attached to oxygen and nitrogen, and there were hydrogens attached to nitrogen and oxygen, it would be a polar molecule. It would have a lot of polar covalent bonds. What if I had a molecule that was all carbon and hydrogen? In this case, these guys, their electronegativities, this marker, are about equal. It's not exact, but they're close enough that they share their electrons equally. So if you have substances that are made out of hydrogen and carbon, they're called hydrocarbons. Okay, so that makes sense, right? Those are non-polar covalent bonds. Fat molecules are hydrocarbons. Lots of carbons, lots of hydrogens. All equal sharing, they're non-polar. If you take olive oil and dump it on water, what's going to happen to it? Where does it go? It just floats on the top, right? It's just floating on the top because it doesn't, first of all, it has to do with density, but it doesn't have any charge. So when things interact with one another, it's because the charges are causing it to come together. It doesn't interact with water because it's not attracted. It just sits on the top. It just is like, well, we have nothing in common. Okay. This I put in there in case you want to know more about this, because I always have students that ask. This wouldn't be something you're responsible for because it's actually very complex, but a lot of students want to know why. Why is oxygen and nitrogen really electronegative, but carbon and hydrogen aren't? Here's some of the factors that you can understand and relate to. It has to do with the size, the physical size of the atom, the distance that those valence electrons are from the nucleus. Okay, and it's actually much more complex, but general trend, if we go up the periodic table of elements, is increasing electronegativity this way. It's not perfect. Okay, fluorine is the most electronegative element. We don't care in biology because we don't have a lot of fluorine in the body. Okay, so we're not worried about it. But we care about these guys. Okay, so our oxygen, nitrogen, carbon, and hydrogen. So water is polar. Oxygen is super electronegative. Okay, and it has a slightly negative charge, and your hydrogens are slightly positive. Here's an example of a nonpolar molecule. Here's the hydrocarbon I showed you. Okay, this would be any molecule that's attached to itself, the same element, like carbon to carbon, hydrogen to hydrogen, nitrogen to nitrogen. Those are always nonpolar. If I have molecular oxygen, that's oxygen covalently bonded to oxygen. They're both really strong. It's like twins, right? One is going to pull it, but the other one is equally strong. Those are always nonpolar because they have the same electronegativities. So far, we're good with all this. We feel like we understand the concept. Bonds are really hard for students for some reason. I haven't figured out the disconnect yet. If you ever want to tell me, that would help me, because then I can help teach it better. Okay, hydrogen bonds are very specific. They occur between two polar molecules. So we all know what a polar molecule is, right? Okay, so you guys are going to be one molecule of water. You are going to be a separate water molecule. So you're a molecule and you're a molecule. We already just went over it. You guys are polar. So somewhere in there you have a hydrogens, you have your oxygen, and you look like this. Right? Positive, positive, negative. This dashed line is showing you a hydrogen bond. It's in between you two. So the easiest definition of a hydrogen bond is a bond between two polar molecules. It's not going to form between a non-polar molecule because it's a charge attraction. Okay, it's similar to an ionic bond. However, it's transient, okay, because this electron is moving. So if the electron is over here and you have this slightly negative and this electron's over here, so this is negative, a bond's going to form. But what happens when the electrons move? Okay, so these move over here and this moves over here. This is no longer negative and positive. The bond is broken. Does that make sense? Also, despite the fact that the electrons are moving around all these atoms, you as a molecule and you as a molecule are also moving. Depends on what we're looking at. If we're looking at liquid water, they're moving. If we're looking at gas phase, they're moving really fast. If we're looking at ice, not so much. Okay, so you have to take that into account as well. If we look at something like cellulose, do you ever get those little strings in your celery? That's cellulose. Okay, so it makes up cell walls of plants. It has thousands, millions of these hydrogen bonds all layered together. That's a very strong connection because there's so many. Think of it like if you put a nail into two pieces of wood, like, man, that's not super strong. If you put 1,000 nails in there, it would be strong. Okay, so that's kind of the idea. So hydrogen bonds can be strong if you have a lot of them, but they're still really easily broken because there's not a lot of energy there, so we can just use an enzyme and pull them apart if we wanted to. They're always represented by a dotted or a dashed line to tell you it's transient. If it's a covalent bond, it's always a straight line. It's going to look like this, double bond, triple bond. Okay, they always look like that. Other place we see hydrogen bonds really important is between DNA strands, which we'll get to on Thursday. This is just for your information because some students just don't know this. You might not have taken chemistry yet, but a couple of things. You guys, we told you molecular symbols. You don't have to memorize those. You probably know a lot of them. The number that is subscript tells you how many, right? So there's 2 oxygens. There's 2 here, 2 hydrogens, 1 oxygen there. There's 4 hydrogens, 1 carbon. Okay, what else to tell you here? Here's the bonds. Okay, this is 1 covalent bond, 2 covalent bonds. That's what it would look like. This is a way of showing you that in nature, a lot of times things exist as rings. We're going to see this when we get to sugars. We sometimes draw them as a line structure, but they're actually in a ring formation. We don't put the carbons in when we do this because we don't need to. Okay? It's like the secret among all biologists. We all know that carbon is the backbone of everything. So if you see lines in a ring like this and there's no letters, you're like, well, what the heck is that? Carbon. Everywhere where you see two lines come together in a point, that's a carbon. Okay? If it's not a carbon, the other examples, it would be oxygen or nitrogen. Then you're going to see the letter N or the letter O. The other thing they don't draw on there are the hydrogens. Because they, again, assume you know. This is a molecule, everything's going to be full. So what's the easiest way to full one hole? This is a carbon. It has bond 1 here, bond here. That means it needs 2 more bonds to fill the valence of 4. That means there's going to be a hydrogen here and here. Okay? Does that kind of make sense? You don't have to do this on a test. I'm just showing you if you look at these structures, you know what you're looking at. All right, solutions. So we're switching gears a little bit. We're going to take what we just learned about bonding and talk about now how does that different molecules or compounds interact in water. Importantly would be in your body is transport because you're multicellular. How are you getting things where they need to go? You're going to put it in your bloodstream. Your bloodstream is water-based. Okay, so we got to think about that. Well, we need a way to dissolve things into water. Or we need to have some protein carry it through this water to get it where it needs to go. So a couple of definitions. Solution. This is a homogeneous mixture of one or more substances. It can't be separated out by filtering or settling. It means it's not like little particles. If you had dirty water and you let it set, some of the dirt might settle down to the bottom because it's big pitcher, substances, clumps of dirt. This would be like you made lemonade. You mixed up your Crystal Light in there with your water. Once it's completely mixed, you shouldn't see the little crystals anymore. They should be all dissolved in the water equally. Okay, now you could do a bunch of fancy science and separate it back out, but we're not going to do that. That's a solution. Okay, so your solute, which would be your Crystal Light, is dissolved in your solvent, which is the water. We say to be fancy because we're fancy, dissolving medium. It's almost 99% of the time water. Okay, water is called the universal solvent because almost everything dissolves in water. Now, not everything, or else we would just be a big blob on the floor, right? We're mostly water. So not everything dissolves in water, but a lot of substances dissolve in water. Solute is whatever we're putting into the water. Okay, so sugar, we can make salt water, we can make Kool-Aid, and whatever you put in your water. How do they dissolve in water? This is all going to get back to the types of bonds that they're made out of. Water is polar, so it's charged. And we know one of the big themes of today is charges are attracted to each other. Positives and negatives attract. So the way that things dissolve in water is through hydrogen bonding. Okay, so that's sort of the key to everything. If we take an ionic compound, so let's think about what that means. Compound means 2 different elements, and ionic means that we have 2 ions. So let's say salt, sodium chloride is an ionic compound. And you guys want to make salt water. So you're going to dump some salt in your water, and you're going to spin it around. The way when you're looking at a salt crystal, what you're really looking at is more than millions of these sodium, then chloride, then sodium, then chloride. They arrange themselves according to negative, positive, just based on charges, and they end up forming crystals. Okay, so that's what you see when you see the little grains. But those little grains are comprised of, billions of these little ions. So when they get into the water, there's still more water molecules than there are ions. So remember, if you guys were sodium and you were chloride, what's going to happen? You're just sitting next to each other because of charges, right? If I put you into water, there's way more water molecules. So the water molecules surround you because they're attracted to you because you're charged and you're also awesome. Okay? All those water molecules get in there and they're going to get between you and they're going to pull you apart. It's going to kind of look like this. Okay, so here would be sodium. You're positive over here, you're cation, so all the oxygens are heading towards you. And there's way more of these, so they're surrounding you. Chloride over here, negative, all the hydrogens are attracted to you. So they surround you. Okay, and this happens throughout the whole crystal of that salt, and it pulls them all apart, all the sodium and the chloride. It still tastes like salt water, okay, because you still have sodium and chloride in there in the right amount. For every sodium, you had a chloride. Okay, they were equal. They're all still there. They're just not next to one another. They still retain the property of salt. They taste like salt. It's just mixed into the water. What happens if, okay, you mix it all in there, it dissolves. It's dissolved now because it's surrounded, and we call this a hydration shell. So that's a bunch of water molecules around each ion. It's a hydration shell. Okay, so you're all in this hydration shell, and then we dump in more salt, and more salt, and more salt. Eventually, what's going to happen, there's going to be too much salt for all the water molecules, and it won't dissolve anymore. The only way to make it dissolve is add more water. Does that make sense? Okay, so you can overcome it if you want to keep adding salt. Okay, doing all that. What about sugar? You have coffee, excuse me, and you're like, okay, I need some coffee with my sugar, right? You're dumping it in there. It's going to dissolve. Sugar is a polar molecule. Okay, so it's a molecule. You're not going to break apart sugar itself. You're not going to break apart sucrose. Okay, so sucrose is what the molecule is. So if you guys are one molecule of sucrose, and you guys are one molecule of sucrose, you guys, quit talking, it's really loud. I know it's not loud to you, but it's so loud to me because the acoustics are so good in this room. Sorry that I interrupted your private conversation in my lecture. Why am I apologizing? Okay. You're a molecule of sugar, and you are one molecule of sugar. So when you look at sugar, it's just like salt, right? These white little crystals. You're seeing millions and millions of molecules all just sort of stuck together. So when you go into hot coffee, what's going to happen is you're just kind of next to one another through charges, but you're not attached to each other. You're your own molecule, and you're your own molecule. So when I put it in there, I just pull you guys apart. You do not come apart as a molecule. All your covalent bonds stay. All of your covalent bonds stay. If you had coffee that's hot enough to dissolve a covalent bond, that'd be a heck of a lawsuit. It would have to be way hotter than your coffee to get it to break a covalent bond. So all you're doing with sugar is pulling apart the polar molecules. What if you had a huge polar molecule? Think of a cotton towel. Your towel absorbs water, or your cotton shirts absorb water, because they're huge polar molecules. It's made out, again, of cellulose. Those are big, big, big molecules. So water's attracted to it, but it cannot dissolve it, which is good, because you don't want your towel to dissolve, or your shirt when you're wearing it and you start sweating. Where'd your shirt go? Dissolved. Okay? That's not good. So that is how that works. It wicks the moisture off of you because it's attracted to it. So you have to be small enough that you can dissolve in water. We're good. Okay, so who dissolves in water then? The whole idea of dissolving was based on charges. So use what you know. This makes sense. If you are a substance that has a charge and you're small enough, you're going to dissolve in water. We call those hydrophilic substances. Hydro is water, you know that. Philic means love. So these are substances that love water. Okay? That simply means they have a charge. So any kind of polar molecule, like a sugar molecule, glucose, whatever you can think of, ions, any ion has a charge, right? It doesn't matter if it's positive or negative, it's charged. Okay, they all will interact with water because of the charges. Water is polar, it always has partial charges associated, so those can all dissolve in water. A hydrophobic, phobic is fear, so these are molecules that fear water. No, not really. You're not going to put your salad olive oil into there and it's going to be like, water, I fear water. No, it just means that it doesn't interact. There's no interaction because a nonpolar substance like hydrocarbons don't have a charge. So there's nothing to dissolve it in water. Water can go around it and just slide back off again. There's nothing to stick it on there. Does that make sense? So think of oils and things. And we'll talk about this, but there are molecules that we call amphipathic. These are big molecules that have sections. So you might have one section that's a hydrocarbon, and you have another section that has a functional group on it that has polar covalent bonds. Think of a cell membrane. We're going to look at the structure of that on Thursday. Has a section in the center that's hydrophobic. On either side of it, it's hydrophilic. So it goes hydrophilic, hydrophobic, hydrophilic. And so those are amphipathic molecules. So a lot of your cell membranes, a lot of your proteins, they're all amphipathic. They have both sections. Here's a good one. You'll like this. See, I told you it was good. You have someone next to you laugh, I don't get it. You should have paid attention. Really just thrown in here at the end of solutions. Concentration, usually expressed for us when we're talking about things as molarity. That just tells you how much solute did you dissolve into a specific amount of your solvent. So we would say molarity is how many moles or how many molecules do you have in a liter of water. And that's usually a concentration. Okay, and you'll see this, and you guys have really fun in nursing field to learn about weight and volume and percentage of all the big fun drugs you're going to give to people. Okay. pH, this is my favorite. pH is really important. The first thing I want you to know, just simplify this. What the heck is it? It stands for power of hydrogen. It's a measure. If I gave you a solution, okay, so I give you this, liter of solution. I don't tell you what it is, and I say, I need you to pH this for me. What I'm asking you to do is count how many hydrogen ions are floating in there. So I have to tell you what a hydrogen ion is. Okay. Hydrogen ion, remember, this thing, is one proton and one electron, right? That's the whole structure of the atom. What's sitting in here is one little positive proton, and out here we had one little negative electron. That's an atom of hydrogen. What ends up happening a lot to hydrogen is it gets stripped of its electron. Somebody, usually oxygen, because oxygen's a big bully, comes over and takes this away. So now what's the charge on hydrogen? It's a +1. It literally is just a proton. So did you guys remember this from biology? When they talk about H+, they just call it a proton, like the proton gradient in the mitochondria. That's just a hydrogen ion. So when we see H+, it's literally just a proton. So that's what we're measuring. How many hydrogen ions are in solution? How many of those do you have just floating around? Why do we care? Mostly because it can kill us. We like to look at things that kill us, right? Especially for patients. Okay? You go in, you're looking at somebody, you take the pH of their blood, and it's off. Okay? You can only go a little bit off of this pH, and you can die. Is your blood is 7.4, right around there. So a little bit above that, a little bit below that is death. Your body knows this, so it has a bunch of systems in place, buffer systems, to help figure this out. So if you don't have enough hydrogen, it'll give the body some. Here, bloodstream, here's some extra hydrogen. If you have way too many, which is normally what happens, because a lot of what we eat is acidic, has a lot of hydrogen ions, then it has to take these away. It has to bind them up into some kind of molecule and get rid of them out of the body. So we want to know, hydrogen ions are very reactive. If you have too many, they'll interact with things like, they'll go into your red blood cells and interact with hemoglobin, and then hemoglobin can't carry oxygen, which is bad, right? So we want to know how many hydrogens do we have in solutions. Okay, the pH range goes from 0, which means the most acidic, the most hydrogen ions that we can have in a solution, to 14, which we call the most basic, meaning the least amount of hydrogen ions. So this is something I'm going to hit upon a lot. The lower the number, the more hydrogen ions you have. Okay, the lower the pH, the more hydrogen ions you have. So 0 is super acidic. Okay, lots and lots and lots of hydrogens. 14, least amount of hydrogen ions. They're both going to burn you really bad if you have a solution like that, but for different reasons. Okay? So, low pH, lots of hydrogens. This is on a logarithmic scale. It's not a linear scale. If I gave you guys $5, you would have 1, 2, 3, 4, $5 bills. Okay, it goes in a line. Log scale goes by a unit of 10. That would be much better to get a log of $5. Okay, so You're going to have 10 times 10 times 10 times 10 times 10. So every time you jump a unit, it's 10 times different. So if I said a pH of 6, it's 10 times different than a pH of 7. 5 is going to be 100 times different than 7. There's a difference of 10 between 5 and 6, and then another difference of 10 between 6 and 7. So it multiplies. So 5 to 7 is 100 times different. Okay. pH itself is defined as the negative log. Okay, so we're using the log scale. These brackets, in case you do not remember this, indicate concentration. Okay, so very specifically, I'm not talking parentheses, like these specific brackets, we use these to tell you this means concentration. So we're saying the negative log of the hydrogen ion concentration. It's negative so that we can have a positive number for the pH. That's the only reason we use that negative. Okay. And I will show you in a minute. So here's the pH number, 0 to 14. Here's the hydrogen ion concentration that goes with it. I don't know if you guys remember this, but if you say 10 to the negative 7, or 1 times 10 to the negative 7, that's the same thing. This is what that number actually looks like. Okay, 6 zeros and a number 1. That's the notation. This, you have to know this stuff. Okay, so if it was 10 to the negative 1, it's 0.1, 10 to the negative 14. This is why, remember we're only looking at hydrogen, that if you have a lower number, you have more hydrogen ions. Okay, so if you look at the concentration of hydrogen, 10 to the negative 1, that's 0.1. That is way more hydrogen ions than this number. It's very small. Do you see that? I don't know. Okay. Here's another chart that's actually good in your book. It tells you the moles per liter. Remember what a mole is. It's just number of molecules. Don't let that freak you out. So how many molecules, or in this case, how many ions do you have per liter of water? Okay, so this is that number. This is what it would look like. 10 to the negative 14 molarity. This is OH, that is H. And this is the P. Oh, this is confusing. This is what it's going to look like in notation. Okay, so 10 to the negative 2, 10 to the negative 3. This will help you if you're not sure. So if we take a pH of 2, let's take 2, and we look at how many hydrogens. Just ignore the hydroxide for now. Well, that's 10 to the negative 2, 0.01, okay, which is written like this or like this. And that's what that number is. If we do a pH of 8, we're looking at this number. So again, this is a lot more. That's a bigger number than this number. So if we're looking at concentration, this is way more hydrogen ions than this. That's an inverse relationship, what I was saying before. The lower the pH, the higher the concentration of hydrogen ions. How am I figuring this out? This is very, very, very easy. If I give you this number and I tell you, here's the hydrogen ion concentration, 1 times 10 to the negative 2 molar. Okay. And you look at that and I said, tell me what the pH is. When you have anything with a base of 10, when you're doing the log scale, all you have to do to figure out the log of that number, it's the exponent. So the log of 10 to the negative 2 is negative 2. You don't need a calculator, okay, unless you're really having trouble seeing that number. 10 to the negative 2. But remember, it's not going to be a pH of negative 2 because we do the negative log. Okay, so why do we do the negative log? Because negative times negative is a positive. Okay, so again, if I tell you the concentration of the hydrogen ions is 10 to the negative 8, the pH is simply 8. It's just the exponent, because I'm always going to give you a base of 10. So if the pH was 10 to the negative 6, or the hydrogen ion concentration was 10 to the negative 6, what's the pH? 6. See, it's like way easy. Don't make it harder. It's very easy. Something that, see if we have time. Okay, we have plenty of time. Great. Okay. Another way that you'll be asked this material, okay, when we look at hydrogen ion concentration, it's in a relationship with hydroxide ion, which is this, OH minus. And it turns out When we measure this at standard temperature, okay, basic conditions, we can look at pure water. We will have a specific number of ions just based on the energy of the water, okay, of how it's going to form an ion versus a molecule. You're going to have a specific number of hydrogen ions and a specific number of hydroxide ions. So in pure water with nothing added into it, hydrogen ions equal hydroxide ions. You have 10 to the negative 7 of each. So what's the pH of that solution? 7. Your neutral solution is going to be 7. Okay, so that means all the ions are equal to all. For every hydrogen ion, you have a hydroxide. That normally never happens because we have a bunch of other stuff always added into the solution, okay, which throws off the number of hydrogen ions because hydrogen is going to interact with it. So if we go this way on the scale, okay, we're going to end up with 10 to the negative 6, right? This would be 10 to the negative 5, negative 4, negative 3. Don't forget the 10. You don't want the whole number negative 3. That would be different than 10 to the negative 3. Whenever we do that, when we change that number, the cool thing is the total number of hydrogen and hydroxides always is going to be 10 to the negative 14 molar. Their product. If we multiply their numbers together, we always get 14. That's where the scale comes from. So no matter what we do, that number should always be 10 to the negative 14 when we have the product of these. So if I had 10 to the negative 4 of hydrogen, I'm going to have, why do I shut the lid? So if this was my hydrogen, my hydroxide is going to be 10 to the negative 10 because those exponents have to equal 14. Remember that when you're multiplying two numbers that have the same base and different exponents, you just keep the base and add the exponents. So 10 to the negative 4 times 10 to the negative 10 is 10 to the negative 14. So if I know my hydrogen ion concentration, I automatically know my hydroxide. In the same sense, if I know my hydroxide ion, I know my hydrogen. So if I told you the hydroxide ion was 10 to the 8, what is your hydrogen ion concentration? 10 to the negative 6, because these exponents are going to add to 14. Okay, this is pH in its simplest form. It's not going to be this easy in chemistry. Okay. So they'll always add to 14. So what is the pH of that solution? 6. Okay. What if I told you the hydroxide ion was 10 to the negative 2? What's the hydrogen ion concentration? Okay, be careful not to say just negative 12, because that's a big number. It's 10 to the negative 12. Okay, so 10 to the negative 12. What's the pH then? 12. It always goes with the hydrogen. Okay, so that's how you figure all that out. It's not so bad, is it? Okay. So if you have a pH less than 7, you have more hydrogen ions in that solution, it's acidic. And remember, the lower you go, the more hydrogen ions you have. If your pH is greater than 7, we call that a basic solution. It actually has more hydroxide than hydrogen. Okay? And it has less hydrogen as you go up, up, up. If you have a solution that has more hydrogen ions than hydroxide, we call that an acid. Okay? If it's a basic solution, it has less hydrogen than hydroxide ion. Something that acts as an acid, if we say, oh, that's an acid, that means when you add it into water, it's going to give off hydrogen ions. So what it's doing is increasing the hydrogen ion concentration. So if I had water and I added an acid, what's going to happen to the pH? Is it going to go down or up? It goes down because you're adding more hydrogens, the pH goes down. Remember, the lower the pH, the more the hydrogen ions. Bases do the opposite. If you add it to water, it's going to attach to freely floating hydrogen ions and take it out of solution. Okay? And then you have less. That's one way a base can work. Another way a base can work is it can add hydroxide ions, okay, which still throws a number off where you have more hydroxide than hydrogen. almost there. We can do it. Okay, OChem, I just briefly mentioned this if you're going to have to take this. This is a whole field of chemistry that's based on carbon. So molecules that have carbon that are attached to hydrogen are usually considered organic. There's a bunch of rules for this. Don't get up to it. I mean, we don't care, right? It's not OChem. But just very basic, if you have carbon and hydrogen, we usually call you an organic molecule. Okay, so carbon, everything like I was telling you, there's 4 areas to make a bond, and carbon always does covalent bonds. Okay, so all things are going to branch off of carbon, and this is showing you all the different ways. We actually have, this is very cool. If we take all the different organisms on life, so I can take a bacteria, I can take a jellyfish, a sunflower, and a cat, and look at the proportions of carbon, hydrogen, nitrogen, and oxygen, and also phosphorus and sulfur. If I look at those elements and what proportions they're in, they're the same for all life on Earth. So that's like Mother Nature taking all the same ingredients and making a cat and a jellyfish. Super cute? Not so much, right? So if I gave you guys like eggs, milk, flour, butter, and sugar and said, okay, everybody has to make a different dessert, it's going to be hard. Okay? Nature can do it because there's all these different ways to connect these atoms to carbon. It's just showing you the different structures. Different structure, different function. What we're going to get into on Thursday is something called functional groups. So in this case, we're talking about all molecules. So what kind of bond are we talking about? Covalent bonds. Okay, so these are all made out of covalent bonds. These groups are called functional groups because we see them over and over enough that scientists sat down and said, hey, let's define these things. If we see a specific group attached to each other, like for example, hydroxyl is this right here. We see an oxygen to a hydrogen and attached to some kind of carbon-based molecule. Anytime it has this group, it becomes soluble in water. Okay, so we started classifying these groups as functional groups. And there's properties to each group. Your book goes in the chart through 1 through 7. I added in methyl because it's a really important one that they clearly did not want to put in. But you'll see these over and over again in chemistry. You'll see them in A&P. I am just going to introduce them. Hydroxyl is not the same as a hydroxide ion. This is attached. This is all covalent bonds, so it doesn't have a negative charge. There's a carbonyl group that we're going to see in sugars. It's a double bond of carbon to oxygen and 1 hydrogen. This is another carbonyl group. It's in a different spot. So these are aldehydes and ketones. Maybe you heard of ketose and aldose. Those are different types of sugars. Carboxyl groups. If you took these 2 groups and put them together, this is what it's going to look like. Here's the hydroxyl. Here's the carbonyl. They form one functional group called carboxyl. So carbonyl, hydroxyl, carboxyl. Amino group is NH2, that's in your proteins. In ester, we find in our lipid group, so this is a carbonyl group attached to oxygen and another group. Sulfhydryl, that's sulfur and hydrogen, and then phosphate group, okay, which is on like ATP. Okay, so that's a really quick intro. We'll go on that in more detail on Thursday, and then we're going to do all the biological molecules, like the proteins, the lipids, nucleic acids,